Hey guys, welcome back to another video. So in this video, I'm going to be working through a couple of examples demonstrating how to solve a first order non-separable differential equation using integrating factors. So in the previous video, I derived an expression for an integrating factor, and we said that it is a function of x that we call mu, and it's equal to the exponential of the integral of a of x dx, where a of x is simply the function coefficient in front of our y whenever our differential equation is in standard form. So the first thing that we need to do is we need to get our differential equation that we're trying to solve into standard form, and then we take this coefficient in front of our y and we take the integral of that with respect to x so that we can obtain an expression for mu of x, and then we can multiply through our differential equation by mu of x and then solve from there. So let's go ahead and demonstrate that with this example right here. So the first thing that I need to do is get this equation into standard form so I can determine my integrating factor. And I can do that by clearing the coefficient in front of our y prime. So if I divide by x squared, what I get is y prime plus 1 over x times y equals 2 over x squared. So we can see that this is now in standard form, where this function right here in front of our y represents our a of x. So I can come up with an integrating factor for this differential equation as mu of x is equal to the exponential of the integral of a of x, which is just 1 over x, dx. So this is equal to e to the natural log of x, where the e and the natural log cancel out, which just leaves me with x. So our integrating factor, mu of x, is just equal to x. So now what we want to do is we want to multiply through our entire differential equation by our integrating factor, x. So we have x times y prime plus 1 over xy equals 2 over x squared. And when we multiply through both sides by x, what we get is the differential equation x times y prime plus y is equal to 2 over x. So now we can integrate both of these sides right here with respect to x. So the integral of x y prime plus y is just equal to our integrating factor times y, which is just x times y. And again, this comes from the product rule. We let u equal y and we let v equal x, where du dx is equal to y prime and dv dx is equal to 1. So this left-hand side expression comes out to be v u prime plus v prime times u, which we know to be u times v prime. So when we integrate this side, u times v prime, all we get is u times v, which comes out to just be x times y, which is why I got this right here. So anyway, coming back to our example, the left-hand side integrates to x times y, which I just showed here. And the right-hand side comes out to be 2 times the natural log of x. And we can't forget our constant of integration. So now all I have to do is divide both sides by x, and what I get is y is equal to 2 over x, natural log of x, plus c over x. So this expression right here is our general solution to this differential equation. And we solve this by taking advantage of using an integrating factor. Now I do want to point out that if we tried solving this differential equation in a different way, like if we tried to separate this differential equation and solve it with straight up integration like we have been doing in the previous videos, then it would not work. And it would not work because we can't separate these variables. No matter how hard you try to isolate the y's and the dy with the x's and the dx, you won't be able to do it. Therefore, we have to consider the strategy that uses an integrating factor. So I want to go ahead and take a look at one more example. Now you guys may recognize this differential equation as an example that I used in a previous video when we were talking about separable differential equations. So technically this is a separable differential equation. I could rewrite this as dy dx is equal to x times y plus 1, and then I could rearrange this to dy over y plus 1 is equal to x dx, and then I can straight up integrate this. But what I want to show for the sake of this example is that we don't necessarily have to separate this using this straight up integration technique. We could still use an integrating factor. And that's because the method of integrating factors will always work for a first order linear differential equation of the form y prime plus a of x y equals b of x. So let's go ahead and demonstrate this. We know that our integrating factor, mu of x, is just e to the integral of negative x dx, because this negative x coefficient is our a of x expression. So our mu of x comes out to be e to the negative x squared over 2. And for those of you who are wondering why I do not include a constant of integration, like a plus c right here, it's just because when I multiply through this equation, it's all going to cancel out. So there's no point of actually writing plus c. So let's go ahead and multiply through our differential equation by this integrating factor. So what we get is e to the negative x squared over 2 times y prime minus e to the negative x squared over 2 times x times y. And this is equal to x e to the negative x squared over 2. So now I can integrate both of these sides. And by taking advantage of the product rule, I don't even have to think about this integral because I know exactly what it's going to evaluate to. This integral is just going to come out to our integrating factor times y, which is y e to the negative x squared over 2. And this right-hand side, we have to do a little bit of u substitution. So if we let our u equal negative x squared over 2, then our du would be negative x times dx. And there should be a dx right here as well as right here, since we're integrating both sides with respect to x. So anyway, when we perform this u substitution, what we get is the integral of negative e to the u times du, which just comes out to be negative e to the u, or negative e to the negative x squared over 2. So let's go ahead and write this expression for the integral of the right-hand side, which is negative e to the negative x squared over 2. And we can't forget our c, so we have a plus c. And now all we have to do is divide both sides by e to the negative x squared over 2. So when I do that, I get y is equal to negative 1 plus c e to the x squared over 2, where the negative goes away because it flips up from the denominator. So this right here is our answer to the solution of this differential equation. And recall that this is the same solution that we got whenever we solved this using the separation of variables like up here. So anyway, that's all I wanted to say about this. Feel free to leave a comment if you guys have any questions, and I'll see you guys in the next video.